This is section 4.1, number 34. Again, we're dealing with a non-homogeneous second order linear differential equation. The non-homogeneous term is a t-squared term. I'll refer to this equation as star. Step 1, we find the solution of our homogeneous problem. We're trying a solution of the form e to the st. We take the second derivative and first derivative, plug it into our homogeneous problem, associated homogeneous problem, and we get our characteristic polynomial, which factors to give us two values of s, -1 and -2. We therefore have our solution of our homogeneous problem written this way. Step 2, we have to find a particular solution based on the form of the non-homogeneous term being a polynomial of second order. We have to try a polynomial of second order with all of its lower terms. So we try an at squared plus bt plus c. Plugging in, we're going to need the first derivative, which is 2a, t plus b, and the second derivative, which is just 2a. Plugging in, we have a 2a for the second derivative. Here's 3 times our first derivative plus 2 times the function itself. That's supposed to equal t squared. We collect the t squared terms, the t terms, and all the constant terms, and that's supposed to equal to t squared. Well, the equation would then say the coefficient of the t squared, which is 2a, has to equal the coefficient of the t squared, which is a 1, and we have this equation. We're going to call it equation 1. The coefficient of the t term has to match the coefficient of the t term on this side. There is no t term on this side, and so 6a plus 2b equals 0, and similarly the constant term has to be a 0. Equation 1 tells us that a is equal to a half. Equation 2 tells us if a is a half, then b is minus 3 halves. And then plugging a half and minus 3 halves in to the third equation tells us that c is positive 7/4. So recapping, here is our second order linear non-homogeneous equation. The general solution will include the solution of the homogeneous part plus the particular solution. Here it is written. Here is our general solution. I only need the y of t. I don't need the derivative, otherwise known as the velocity v of t. But in order to find a particular, to solve the initial value problem, I am going to need to make use of the velocity, otherwise known as y prime. And so taking the derivative of y, I have this, and then my two initial conditions that were given said that y at 0 is 0 and y prime at 0 was 0. Plugging in 0 into y of t, I have a k1, a k2, and just a 7/4. Plugging in to y prime, plugging 0 into y prime, I have a minus k1, a minus 2k2, and a -3 halves. Solving for k1 and k2, if I didn't make a mistake, I have that k2 is minus 13/4, and then k1 ends up being just a 5. Okay. So the solution of our initial value problem is given like this. And then the final thing in part C, they ask us to make a sketch. When making a sketch, what's significant really is what happens as t goes to infinity. These terms, because it's e to the minus t and e to the minus 2t, as time goes on will disappear. The dominant term is the t squared term. 1/2 t squared term is our dominant term. Using my calculator, I have actually made a rough picture of what we look like. It never touches the axis here, but it does start at a value of, let me think here for a second. It should be starting at 0, and so I'm not sure why I'm drawing it up here at 5 or above 0, but it should be starting at 0. I can't erase what I've already drawn there, but in the end, the long-term behavior and what I'm looking for is that it looks like a quadratic. If I were to make a graph in red of 1/2 t squared, I would see a picture. I apologize, I can't make it continuous with this pen, but this picture essentially, this is the graph of 1/2 t squared, and if I didn't have a calculator, that's all I would be looking at. I'd be looking at what is the largest term, the dominant term, and it is 1/2 t squared, and that's what I would draw as my basic behavior of my solution. Okay, I hope that helps. Good luck.